So we're going to continue to look at integrating, and we're going to look at some indefinite integrals and some definite integrals, but we're going to look at problems that are maybe not as straightforward, a little bit more challenging. Now, looking at this problem here, you might be able to see how to do it off the top of your head, but I'm going to go ahead and do something a little bit different that may help all of you, and it's going to introduce a way that will work on all problems. You don't always have to use this, but it can work on problems. I'm going to let you just be what's on the inside. Well, I have a dx showing up, so I got to go ahead and take the derivative of this. Well, if I do the derivative of the left side, I get a du. Derivative of the right side, I get a 2 dx. Well, I just need a dx to show up here, not a 2 dx. So I'm going to get dx by itself by multiplying both sides by a half. So I'm going to rewrite this. So instead of writing the red, I'm going to write that with a u. So I would have u still to the fifth power. Instead of writing dx, I'm going to write what dx is, which is a 1/2 du. Now, we are multiplying by this 1/2. If you're multiplying by a number, we can pull that 1/2 out in front of our integral. Then we're just having u to the fifth power du. Well, that's pretty easy to integrate. We'll just leave that there. We have to increase our exponent by 1, and then have to remember we have to have a 1/6 in front to undo that 6th power if you did take the derivative. Being an indefinite integral, remember plus c. Well, we get 1/12 u to the 6th plus c. Well, all we have to do is plug in what u is, because we started out with x's. We want our answer to leave or end up with x's. And so we would just have this as our answer. Now, some of you may have been able to see this without using a u, but introducing u here on an easier problem will help you as we get to more challenging looking problems. Here we have variables times variables, so you can't just integrate each piece, because remember, if you're doing derivative, you have to use a power or product rule when you're multiplying, and so it gives you a plus, and so it doesn't work to just do each piece. Now, when you're selecting u, you typically want u to be the higher exponent. So we have this option here of 1 plus x squared, or this option here. So you typically want u to be the higher exponent. Well, we have a dx showing up, so you want to go ahead and find your derivative of this. So we get a du is equal to, that goes to 0, and we get a 2x dx. So looking at this, this is your u. All I'm going to do is, because we're multiplying, I'm going to, instead of having my 2x here, I'm going to move it back with my dx. I did that because now that blue 2x dx at the very end matches perfectly with my du. And my u is what's in red, raised to the 1/2 power, because it's a square root. Now what I have here is pretty easy to integrate. I just increase my exponent by 1, undo the derivative, or undo my exponent in front by doing the reciprocal, and being indefinite, I need to do plus c. One last thing we do at the end is, since we started out with x's, we want our answer to be left with x's, so you have to replace u with what u is, of a 1 plus x squared. Once again, here we're multiplying variables, so you're probably going to have to use a u. You have the option of u being what's on the inside or u being what's in front. Typically, you want u to be the higher of the two exponents, so we're going to let u be this. Well, to get your du to show up, you need to go ahead and do the derivative of u, and you get a du. Do the derivative here, you get a 3x squared dx. Well, you'll know that we have this. If we put our x squared with our dx, we have this. We don't want this 3 showing up. So let's multiply both sides by a 1/3. So I can have my integral sign, my u to the 1/2, because that was the red inside my root. And then instead of writing this blue right here, I'll write what that blue is, which is a 1/3 du. Well, in integrating this, we're timesing by 1/3. We can pull that 1/3 out in front of our integral. We're now just integrating u to the 1/2. Well, that's pretty easy to do. You increase your exponent by 1. Undo that, so put a 2/3 in front. Indefinite integral, you have to go plus c after you integrate. And now you know that 1/3 times 2/3 is 2/9. All we have to do then is replace u with what it is in terms of x, because we started out with x's, and we will get this. So over here, you have some options of what u could be. U could be either the 3x, you could let u be the cosine of an x squared, or you could let u be the x squared. Those are really kind of your options of what u could be. Well, I'm not going to let u be this first one, because if I, or the middle one, because if I did the u being this and I get my du, I would have a sine of this showing up, and then the derivative of the inside with a dx at the end. Well, I don't have any sine showing up, so I know it's not going to be this. If I let u be the 3x in front, it's not going to help me because I'll still end up with variables times variables. Once again, you typically want u to be the higher of the two exponents. So of what's left, you want u to be the higher of the two exponents. So you want your u to be your x squared. Now, once again, we were just timesing by 3. So I'm going to go ahead and move that 3 in front of my integral. Let u be the higher of the two, so this would be my u. Well, if I do my derivative of u, I get du is equal to a 2x dx. Well, the only thing I had left, because I pulled out that 3, would just be an x dx. So I don't want this 2 showing up, so I'm going to multiply both sides by 1/2. So I'm going to take my x dx and replace it with a 1/2 du. So I'll still have my 3 in front, still have my cosine. Instead of writing x squared, I'm going to write u. Instead of writing x dx, I'm going to write out what x dx is, which is a 1/2 du. Once again, now I'm multiplying by a half, so I can pull that half in front with my 3. I get 3/2. Now I just have the integral of a cosine of u du. Well, at this point, you should realize, oh, I know how to integrate cosine. And so you could integrate it, you get sine of u. Being an indefinite integral, after you integrate, you need to go plus c. Now, your last step, just plug in what your u is, and we would get this. Now, this one could be done with a u, does not have to be. You might be able to think, oh, I know the derivative of what gives me secant squared. You know that that is tangent. And then you have to remember, oh, I have to undo the derivative of the inside, so I need to have a 1/3 showing up. So do you always have to use an u? No. Sometimes you can just see how to integrate them off the top of your head. This happens to be one of those. So it can be done either way on some problems. On other problems, it's a lot easier if you go ahead and use a u. So here, I'm going to pull my 2 in front because I'm timesing by 2. So now you have some options of what u could be. You could let u be equal to your sine of x all cubed. You could let u be equal to the sine of x, or you could let u be equal to your cosine of x. You could do either one of these for your u. Well, if you let u be this bottom one, you get your du to be a sine of x dx. Well, if you did that, you would then have your du being cubed here. We've never dealt with that, so that's not going to work. So we could maybe try u being this. If we did that to find our du, we'd put the exponent in front, decrease it by 1, chain rule, derivative of the inside with a dx. So if this is our u, we only want a cosine showing up rather than this, all this stuff. So that's not going to work. If we let u be your sine, when we do our du, that gives us cosine. Oh, well, this would just be our du right over here. The cosine of this is our du. So that works out kind of nice. So that matches with our du. We'd have the sine cubed. So we go 1. U, once again, is sine being cubed. Your cosine dx is your du. Well, now this is pretty easy to integrate. We'll leave our 2 in front. Increase your exponent by 1. Put a 1/4 in front. Remember, plus c. Well, 2 times a fourth, you know, is a half. Plug in what your u was, which is sine. So sine to the 4th of x plus c. So sometimes you have to write out some options of u to see which one makes sense in the context of your problem. So we did go ahead and look at this problem right here. This was an indefinite integral. However, here it's a definite integral. So really, all you have to do is your normal integration. Instead of redoing it, we'll just copy down the answer, which was this here. Being a definite integral, all you have to do at the very end is just evaluate it from 0 to 3. So you do your normal u substitution if needed on a problem, if it's a definite integral, and then at the very end you do your evaluation. So you plug in your 3 minus what you get when you plug in your 0. And so you could type this line in all at once on your calculator, or you could do it by hand, but either way you would get 42. So let's look at this problem, which is a definite integral, in which we have not done before. Now here, there's not an option to say, well, u is going to be the higher of the two exponents, because we're dealing with trig functions. It doesn't always work, but you often want u to be what's on the bottom. So I'm going to let u be what's on the bottom. So if I go ahead and do that, I would get my u on the bottom. Well, if I do this and do my du, I go du, derivative of 1 goes to 0, derivative of this. So now you'll notice with what I have, this, I have a 2 hanging out. And notice with what we have here, we don't have a 2 hanging out in front of it. So we'd have to multiply both sides by a half. So this is what we have. I'm going to replace that with a 1/2 du. But keep in mind, being a definite integral, we started out with t's. If we are going ahead to rewrite this in u's, we have to change our bounds so that our bounds match with our variable. Our original bounds were t's, and that works great when your input is t. But when your input becomes u, you got to change your bounds. Well, if t being 1/4 here, if t is 1/4, you plug it into what you had for u, which was 1 plus sine of 2 times your input, so 1 plus sine of 2 times your input. Well, 2 times pi over 4, you know it's pi over 2. Take the sine of that, which is 1, plus your other one in front, you get u to be that. So instead of writing pi over 4, when you write it with u's, you got to change your bound to match your variable. So you want to also go ahead and say, oh, well, this is my t being 0. When t is 0, I plug it into my u, which is 1 plus sine of 2 times 0. And so we get u to be 1. So when I rewrite this from t's right here to u's, my lower bound is 1. So at this point, all I have to do is simplify this a little bit. I can pull my 1/2 in front, still with my bounds, and I have du over u. Well, remember, when you're integrating du over u, that's your natural log. And then we just have to evaluate that. Now, could you at this point go ahead and rewrite this in terms of t's again, substituting in what your t is here and changing your bounds back to these t's here? Yes, but you don't need to. Since we changed our bounds because we were dealing with u, all we have to do is take 2, plug it in, minus what you get when you plug in 1. Well, you should remember that the natural log of 1 is 0, so that drops out, and we just get 1/2 natural log of 2. So let's take a look at this problem here. So suppose we have this. We don't necessarily have a higher exponent, so it doesn't work to be able to use that trick. In this situation, we're going to let u be what's on the inside. That'll be the easiest. Well, if you use what's on the inside, I would get this. Well, I don't have a 2 showing up in my problem outside of my u, so I don't want that 2, so I'm going to have a 1/2 du showing up. So as I look here, this is going to be my 1/2 du I just came up with. This is going to be my u to the 1/2. But I got an x showing up in my problem. And I don't have x in this stuff. So really, all you want to do is take this right here and solve it for x. So you go u plus 1 is equal to 2x. And then to get x totally by itself, you could multiply everything by 1/2. And I would encourage you to multiply by 1/2 versus going divide by 2. So instead of writing my green x over here, I'm going to write a 1/2 u plus 1. Oh, so now I have a 1/2 I'm multiplying by here, another 1/2 I'm multiplying by here, really gives me a 1/4 in front. Still with my green, still with my red, and my du. Now I still have variables times variables, but now I can easily distribute that red into the green. And so I would get u to the 3/2, u to the 1/2. Now I can go ahead and easily integrate this, leaving that 1/4 in front, increasing my exponent by 1, and putting a 2/5 in front, plus increasing my exponent by 1, and going plus c, because it's an indefinite integral. Now, we do not want to leave our answer with u's in it. But before we substitute in what u is, we're going to simplify this. You know at this point you got to pull out the higher of the 2 exponents here. But we also have fractions here. I would go ahead and rewrite these with using my common denominator. Common denominator would be 15, so you multiply the first fraction top and bottom by 3, the second fraction top and bottom by 5. You get this. Now you can pull out the over 15. What can you pull out of the top? Between the 6 and the 10, you're going to pull out a 2. And when you're looking at the u's, you pull out the smaller of the 2 exponents. Well, what's that leave you with? You pulled out the over 15, you pulled a 2 out of the top, leaves you with a 3. And then it would be a u to the first, plus you pulled out the over 15, you pulled a 2 out of the top, leaves you with a 5, and we pulled the u out. Well, in front, we could simplify that. We get 2 over 60, which is 1 over 30, still with our u, and we have this. Now I would go ahead and plug in what my u was from my original problem, which was this, plug it in here. Now all I'm going to do is simplify this. I'm going to distribute the 3 into the red, collect my like terms, and now I am done. Now, if you wanted, however, notice you could take a 2 out of here. If you factored a 2 out of that, you would get this. But if you pulled a 2 out, you'd have 2 over 30, which is a 1/15. I'd prefer the bottom one, but I would probably also accept the second from the bottom one. So try this one here. Now I'm going to let u be what's in my root, so I can find my du. I get this here. Notice I don't have an extra 2 showing up in my problem, so I'm going to go ahead and go 1/2 du. So this is my u, this is my 1/2 du. Doesn't help me with this, so I need to go ahead and solve it for x. So to solve this for x, I'd have to add 1 and then get rid of that timesing by 2. So when I do that, my u is the red, what's on the bottom, so it's u inside my root. My du, or dx, is my 1/2 du. Now my x right here in green is that 1/2 u plus 1. But being a definite integral, rewriting it in terms of u, I got to change my bounds. So if x is 5, and I got to plug it in here to find my u, 2 times 5 minus 1, 2 times 5 minus 1, well, I get my upper bound then in u's to be called 9. Then I got to take my lower bound of 1, plug it into my u. So I go 2 times 1 minus 1, and I get 1. So my lower bound in u's is this. Now notice we have a 1/2 times a 1/2, so I can pull a 1/4 in front. I'd still have the green parentheses, and then I'm going to have my u to the negative 1/2 because I'm pulling this u to the 1/2 from the bottom up to the top. That's why it's a negative exponent. Now all I have to do is distribute the red into the green. Still haven't done any integration yet. All I'm doing is distributing. Now that I don't have variables times variables in the black down here, now I should be able to do my integration, leaving that 1/4 in front, increasing my exponent on this by 1, remembering to undo that by putting a 2/3 in front. Here, increase my exponent by 1, and then have to evaluate it. Because I changed my bounds to match my u's, I can just go ahead and plug these numbers in. I'm going to go ahead and choose to simplify this a little bit first. So I'm going to rewrite it over my common denominator. So 2 over 1 is 6 over 3. So I'm going to pull out a 2 out of the top, pull out the over 3 in the bottom. I'm going to pull out the smaller of the 2 exponents, and then I'm going to look at what's left. Well, I pulled out the 2/3. I'm going to be left with a u to the first here, plus I pulled out the u to the 1/2. I pulled out the over 3. I pulled the 2 out of the top. Leaves me with a 3. So simplify this in front down to this here. Now I can just plug in my 9 in both spots for my u, minus what I get when I plug in my 1. And so then I end up just plain old getting 16/3.